This chapter is a little bit about introduction to the organic reactions. Organic reactions are a little bit different than what you've learned in Gen Chem, and that's why this chapter is kind of nice to have, okay, just to introduce you to the different concepts and keywords. So in any kind of a reaction mechanism, you have to see how the reaction actually takes place, what bonds are breaking, and what bonds are making as the reaction is progressing. We have to draw a mechanism of the reaction, which is the curved arrow, okay? And then, of course, the big thing is, did a reaction even take place? So you have to be able to predict the possibility of a reaction, draw the mechanism, break the right bond, form the right bond. Okay, that is what is called a reaction mechanism. In organic chemistry, there are four main kinds of reactions: addition, elimination, substitution, and rearrangement. In an addition reaction, you take something that is not saturated, which means anything that has sp and sp2 bonds, and then add a small molecule to it or a large one, and then add to that double bond or that unsaturation, and you get an addition product. Okay, and so typically you will end up with something that is saturated, something more like an alkane. In elimination reaction, you take something which is saturated and you remove a small molecule, which ends up giving an alkene or an alkyne, depending on what you're removing, and of course a small molecule. Okay, that is the one that was eliminated. Addition and elimination, these are opposite of each other. So in addition reaction, you're starting with an alkene. In an elimination reaction, you're producing an alkene. The next reaction is substitution, in which case you take one atom and you substitute it with another one. So this is a substitution reaction. Of course, this hydrogen over here, that is called the leaving group, and it's gone now. So that is a substitution reaction. A rearrangement is when you have any molecule that rearranges, which means it's a constitutional isomers. The atoms are still there, but they're rearranged. It's not the same thing anymore. So here the carbon-carbon double bond is a terminal one, but now it's not a terminal one. It's internal, it's in the middle. And this rearrangement can happen in presence of a catalyst, an acid or a base or something else, or light maybe. Will the rearrangement always happen? No, it depends on what kind of a molecule you have. The whole point of rearrangement is to lend more stability to the molecule. So if more stability is possible, it will rearrange. Otherwise, that rearrangement is not going to happen. So these are the different kinds of reactions you will encounter as we go on, and they will become second nature to you. You'll just know them. This is not something that is hard, but you should be able to classify them. So the first thing we have to learn in any kind of reaction mechanism is how the bond breaks and forms. So there are two kinds of bond breakages. One is symmetrical, the other one is unsymmetrical. The symmetric one is known as homolytic, the unsymmetric is known as heterolytic. If it's a symmetric one, it means that there is something equal going on. And so, for example, here in the first case, you have an equal bond breakage, a homolytic cleavage. And in this case, a bond, which is made up of the two electrons, when it breaks, A takes one electron and B takes the other electron. Okay, so which means that each of the atoms get one electron each. So in the product side, you end up seeing two species with equal number of electrons, which is 1 and 1. These species are called radicals. They are not charged species. They are neutral, electrically neutral. And they have a very different kind of chemistry, which we will talk about in one of the chapters this semester, not in this one just yet. The other kind of bond cleavage is what we call unsymmetric or heterolytic cleavage. In this case, what happens is that one of the species will take both of the electrons. And once it takes both the electrons, it means that one of them is left without any electrons. So in this case, A is left without any electrons and B has the electrons. So if B has the electrons, it becomes the anion, and A is left without the electrons, and so it is the cation. So which means that you actually have charged species as a product, okay, in this case. So this is a heterolytic bond cleavage. The bond breaking is also of two kinds, symmetrical and unsymmetrical. In case of bond formation, which is symmetric, both species will bring one electron each and form a bond. In the unsymmetric kind, one species will give the electrons to the other to form the bond. We have done this type of reaction before in acids and bases, whereas the base was the electron donor and the acid was the electron acceptor. Okay, and then you form a bond. So this is an unsymmetric kind of bond formation. These reactions, the heterolytic and bond formation and bond breakage, that's the one we're going to focus on a lot more initially, and then later on we'll talk about radical reactions also. Here is a little review of the arrows that I gave you in the beginning also, and here it is again. So we have a straight arrow, which is for synthesis, for yield. Then this kind of an arrow, which is half going forward, half backward, and this is an equilibrium arrow. If you have a two-headed arrow like this and it is a resonance, please, equilibrium, resonance, not the same thing, okay? So do not draw arrows like this to show resonance. Resonance is very particular and it's only this kind of an arrow. And then if you have a double arrow going like this, then this is a retrosynthesis arrow, which is actually backward. And again, as I said before also, this is very useful for organic because sometimes we actually start from the product and work our way to the starting material. So in that case, this becomes very important. You have to be very careful, okay, when you draw your arrows, because you have to mean exactly what you mean, all right? Draw what you mean. Then this curved arrow over here shows the transfer of 2 electrons. This is a double-headed arrow. And then here, this one shows the transfer of 1 electron. This is a half-headed arrow. Okay, so be careful how you do this. And curved arrows show the transfer. You can't show straight arrows for that. Okay, that is for synthesis. So the curved arrows are the ones for transfer of electrons. Polar reactions. Now, this is the one in which we were talking about that you have a heterolytic bond cleavage. And when you have a heterolytic bond cleavage, it is because a bond can break and it breaks unequally. And the only way it can break unequally is when you have electronegativity difference. If there is a charge separation, then it's easier for that bond to break. If there is no charge separation, which means if it's a non-polar molecule or a non-polar bond, it's very hard to break that bond. So the more electronegativity difference there is, the easier it is to break the bond, which is why we have acidic protons and so on. So here are some examples of the bonds that are actually polar, because these will be important, okay? When we talk about mechanism of reaction, you have to understand which is the positive species and which is the negative species. In organic chemistry, the acids and the bases, the cations and the anions, they're not very clear. So you really have to understand the role of electronegativity in organic. Also the role of this kind of a polar bond that results from there, okay? Because you don't really see a clear charge separation. You will see a delta positive and a delta negative. That tells you that this bond is a polar bond, and that is because of electronegativity. So wherever you see this kind of a polar bond, that's where you know that you have a positive center and a negative center. So when you start drawing arrows, you know where to start from and where to end, okay, your arrow. That's an important part. So here are some other examples. Alkyl halides. Halides, the most polar bond will be, of course, with fluorine, then a little bit less with chlorine, and then iodine. By the time you get to iodine, it's literally a very non-polar kind of a bond, although it will still have some polarity, but not as much as CF or CCl. Amines and then ethers. Here's what the charge distribution looks like. So this is kind of a nice chart to have to understand how the charge separation occurs in organic molecules. And these are all your functional groups that you have learned. In case of a polarized reaction, okay, like this one, for example, as you've done before, there are very specific names given to the species. So you have to learn these names and you have to remember them, because this is how we refer to them all the time, okay? We talked about before regarding Lewis acids and Lewis bases. And Lewis acids are electron acceptors, whereas Lewis bases are electron pair donors, all right? So there are the properties of Lewis acids. So Lewis acid is the positive center because it is going to accept electrons, whereas the Lewis bases are negatives because they give electrons, which means that Lewis acids are electron poor and Lewis bases are electron rich. The Lewis acids are usually referred to as electrophiles. Electrophile meaning electron loving. electron is negative, so it is negative loving. And the Lewis bases are called nucleophiles, nucleus loving. Nucleus is where the positive charge is, so nucleus loving. It doesn't really go to the nucleus, but it's just a reference that you know it's positive. So it's a nucleophile. From now onwards, we will refer to the Lewis acids and Lewis bases as electrophiles and nucleophiles. We still refer to the acid and bases also, but electrophile and nucleophile are a more common term to use for positive and negative centers, okay, in organic chemistry. So here we have a negative species, which is then the nucleophile, electron rich. It attacks the acid, which is the electrophile, electron poor species. Once it does that, here is the new bond formation. Okay, and remember, a bond will always have a pair of electrons, and when you're transferring these electrons, this arrow that's going over here, that is transferring a pair of electrons, because see the double-headed arrow, okay, over here. So that is what we call a polarized reaction, and this is the most common kind of a reaction you will see in organic. Just a little bit more about the arrows in reaction mechanisms is that arrows are there to keep a track of your electrons. And sometimes I know you will forget to draw the arrows, but I encourage you to draw the arrows as much as possible. Even though you know what you're doing, but I don't know what you're doing. So you have to draw the arrows to show me which bond is breaking and which one is forming, okay? So it's a very good way to track the movement of your electrons, okay? And the key is to start your arrow from the electron-rich species, which is the Lewis base, which is also the nucleophile, and take it to the electron poor species, which is the Lewis acid, also the electrophile. Okay, so always from negative to positive. Okay, that is how it goes. So if you have an arrow going from oxygen to the E over here, that means these electrons are being transferred, and it's not like they're being transferred. It means this is the bond that is actually forming, okay, over here. So that is the bond formation going on here. And this is how you draw the arrows for all these different species, because what this shows you here actually is not all the fact that you have arrows, but the fact where the electrons are coming from. So here in this case, the electrons are coming from the lone pair. Here they're coming from the lone pair also. Here they're coming from a charge, okay, which is carbon anion. So this is a negative charge. And here the electrons are coming from a double bond, okay. And so all of these electrons can be given away, and they are going to the electrophile. E is the electrophile. And all the other ones, these are where the electrons are. This is the nucleophile. So right here again, another type, another example. Okay, here is your nucleophile, which goes for this proton, which means that this bond is forming. This electron goes to bromine over here, which means that this pair of electrons is getting transferred to bromine. And so then the product is the new bond, which is between oxygen and hydrogen, and then the electrons that were between hydrogen and bromine now belong to the bromine. Okay, so this is how you would write a mechanism. You can also go back to the acid-base chapter and look in there, because some of the mechanism was covered there also. It's the same kind of a thing. One last thing about mechanisms of reactions is kinetics. And I know kinetics was in Gen Chem 2 for you, so please review that if you've forgotten your kinetics. In kinetics, we have different orders of reactions, speeds of reactions, and how reactions are affected by different things like temperature, time, concentration, and so on. In organic chemistry also, kinetics is a big thing, okay, in which we talk about how to control any kind of a reaction rate. And most of all, kinetics actually helps us to establish how a reaction mechanism takes place, okay. And so if you remember from this diagram that you learned in Gen Chem 2, is that this is the kinetics diagram, okay, where you have energy as one scale and the reaction progress going on in the other one. And so you have this curve, okay, and in this curve, this energy curve, you have the starting point right here. It takes activation energy to get to the transition state, which then goes down, okay, to give you the products, all right. And this is only part of the product. We're still not quite at the product yet, all right. To get to the transition state, you need a minimum amount of energy, which is called the activation energy. And the transition state is, of course, very high in energy, much higher than the reactants or the products, okay, or any intermediates that are formed. You can have one transition state or two transition states. And as we go on and learn more about mechanisms, we will learn about how many transition states are formed. And if they do, what does it mean, okay, for us? Regarding these energies over here, I will probably not talk too much about these energies, but it doesn't mean they're not there, okay? The energies are there. The free energy, entropy, all of those things have a meaning, but I'm not going to get too much into it. However, we will get into the order of reactions, okay? And so if you want to go back and review order of reactions and your kinetics graph, then please do that. Your keywords for this chapter, different reaction types, okay, that we have, and then polarity of the bond, which we also did in chapter 1, okay, so that's not something new. You should be able to identify which atom is positive, which one is negative, electrophile, nucleophile, what are those two things, and if a bond cleavage is going to be heterolytic or homolytic. A little bit about mechanisms and transition states. We really have not done too much over here, so I'm not going to ask you yet about transition states and activation energy. That will come in the next chapter.